J square upon j omega is 1 upon c1 plus 1 upon c2 is equal to minus j omega L. 1 by c1 plus 1 upon c2 is equal to omega square L. c1 plus c2 upon c1 c2 is equal to omega square L. 1 upon c equivalent is square L. Equivalent capacitance is equal to c1 c2 upon c1 plus c2. F is equal to 1 upon 2 pi square root of L C equivalent. Calculate the oscillator frequency for the FET RT oscillators for the following circuit values. C is equal to 250 picofarads, L2 is equal to 1.5 millihenry. Equivalent inductance is equal to L1 plus L2 plus 2M equal to inductance is equal to 3 millihenry. M is the not given, so that assume M is equal to 0. F is equal to 1 upon 2 pi square root of L equivalent into C. F is equal to 1 upon 2 pi square root of F is equal to 1 upon 2 pi is equal to 0.183 megahertz. Calculate the oscillation frequency for the transistor Hartley circuit having the following circuit values L2, M and C. Equivalent inductance is L1 plus L2 plus 2M Henry. Equivalent inductance is equal to 1.65 millihenry. The frequency of oscillations is F is equal to 1 upon 2 pi square root of equivalent inductance into C. 1 upon 2 pi square root of 1.65 10 raised to minus 3 into 150 into 10 raised to minus 12. F is equal to 1 upon 2 pi into 10 raised to minus 7. F is equal to 0.320 megahertz. FET Colpitts oscillator is having following circuit values. Determine the circuit oscillation frequency. F is equal to 1 upon 2 pi square root of C equivalent into L. C equivalent is C1 C2 upon C1 plus C2. F is equal to 1 upon 2 pi square root of C equivalent into L is equal to 1.47 megahertz. The characteristics of a crystal. The quartz crystal, when mechanical stress is applied at the two faces of the crystal, the voltage is generated at the opposite faces of the crystal. This effect is known as the piezoelectric effect. When voltage is applied at the two faces of the crystal, that causes the mechanical distortion in the shape of the crystals. If an alternating voltage is applied to the faces of the crystal, the mechanical vibrations are set up. This is equal to the natural resonance frequency of the crystals. The electromechanical resonance characteristics of the crystal is represented as the electrical equivalent resonant circuit. The series RLC circuit in parallel with a mounting capacitance Cm. Resistance R is due to the internal friction in the crystals, and inductance L is due to the mass of the crystals, and capacitance is due to the compliance of the crystals. The Cm is due to the mounting of the crystals. So that R, L and C, and here it is the mounting capacitance of the crystals. Resonant frequency of crystals, series resonance. At resonance, the reactance of the elements in the series circuit are equal. At resonance, the reactance of the elements in the series circuit are equal. The impedance offered by the circuit at resonance is low, and it is equal to the resistance R. The series resonance frequency is also low. The reactance of the elements L and C are equal in magnitudes. The reactance of the elements in the series circuit are equal. The impedance offered by the circuit at resonance is low, and it is equal to the resistance R. The series resonance frequency is also low. The reactance of the elements L and C are equal in magnitude, so that is equal to omega upon C. It is equal to F is equal to 1 upon 2 pi square root of LC, and it is the series resonant frequency. Now it is the frequency versus the impedance, so that the impedance offered by the circuit at series resonance, it is equal to less, and the series resonant frequency is also less. And the impedance offered by the circuit at series resonance, it is equal to less, and the series resonant frequency is also less. The parallel resonance. The reactance of the elements in the series circuit are equal to the reactance of the mounting capacitance at resonance. The impedance offered by the circuit at parallel resonance is high. The impedance offered by the circuit at parallel resonance is high. The parallel resonance frequency is also high. The impedance offered by the circuit at parallel resonance is high and the parallel resonance frequency is also high. The reactance of the inductance L is equal to the reactance of the capacitance C, so that the modulus of XL is equal to XC plus X. Square is equal to 1 upon L, 1 by C plus 1 upon Cm. Is equal to F is equal to 1 upon 2 pi square root of L C equivalent. C equivalent is equal to C into Cm upon C plus Cm. The crystal oscillators. A crystal oscillator using a transistor is as shown in the figure. The resistances R1, R2 and Re are the DC biasing elements. Resistance R1, R2 and Re are the biasing elements for the transistors. The RFC coil that isolates the AC signal and the DC signal at the outputs. The RFC coil that isolates the AC signal and the DC signal at the outputs. The bypass capacitor CE is connected in parallel with the resistance Re. Crystal is connected in series. Crystal is connected in series with the coupling capacitors. Here crystal is connected in series with the coupling capacitors. Both the elements are present in the feedback path from the collector to base. Both the elements are present in the feedback path from the collector to base. The coupling capacitor blocks the DC component at the outputs. The impedance offered by the crystal is low. The impedance offered by the crystal is low. The positive voltage feedback from collector to base results in the oscillations at the outputs. So that the positive voltage feedback from collector to base results in the oscillations at the outputs. Because here it is a positive voltage feedback and the impedance offered it is also low, so that results in oscillations at the outputs. The variations in the parameters of the transistors does not affect the frequency of oscillations. The variations in the parameters of the transistors does not affect the frequency of oscillations and remains stable. For frequency stability of oscillators, crystals are used. A crystal has L is equal to 2 Henry, C is equal to 0.01 picofarad and R is equal to 2 kilo. Its mounting capacitance is 2 picofarad. Calculates its series and parallel resonating frequency. Fs is equal to 1 upon 2 pi square root of Lc series resonant frequency. C is equal to 1 upon 2 pi square root of 2 into 0.01 into 10 raised to minus 12. Fs is equal to 1.125 megahertz. Fp is parallel resonant frequency. Fp is equal to 1 upon 2 pi square root of L C equivalent. C equivalent is C into Cm upon C plus Cm. It is equal to 10 raised to 2 into 10 raised to minus 12 is equal to equivalent capacitance is equal to 24. Equivalent capacitance is 0.0099 into 10 raised to minus 12 farads. The parallel resonant frequency is equal to 1 upon 2 pi square root of here 2 into 10 raised to minus 12. Parallel resonant frequency is equal to 1.13 megahertz. That is the parallel resonant frequency of the oscillators, and that one it is the series resonant frequency of the crystal oscillators. Okay, these are the two frequencies that are determined for the crystal oscillators.